Welcome to Lecture 52, in which we're going to confront head-on this question, is light a wave or is light a particle? And then we're going to ask, is matter a wave or is matter a particle? Because quantum physics now puts us in this quandary, this wave-particle duality, and we somehow have to reconcile this. We either have to answer the question, is light a wave or is it a particle? Is matter a wave or is it a particle? Or we've got to live with the ambiguity that it's both. And so we'll explore in this lecture how that comes about. So let's raise this question, wave or particle? The nature of light. Think about the nature of light. It was in 1801 that Young first convinced the world that light consists of waves. Christian Huygens earlier had thought light was a wave, but Newton, who had thought light was a particle, overruled by virtue of his scientific seniority, his scientific precedence. And so until 1801, light was considered to be a particle. But in 1801, Young showed conclusively that light consists of a wave. How did he do that? He did that by showing that it undergoes interference, and I've got a picture here of an interference pattern. And over here, I have a simple modern-day version of the apparatus that Young used. It's a laser going through a couple of slits and producing an interference pattern. So we can now do Young's experiment very, very trivially in the lab anytime. And I did this experiment back in Lecture 43. So Young shows by means of interference unambiguously that light consists of waves. Fast forward to 1905, and Einstein explains the photoelectric effect by saying that light consists of photons, these bundles of energy that behave, according to the Compton effect, like particles. So which is it? Is it a wave or is it a particle? That's our question. Now we have the same problem for matter. Think about the nature of matter. Democritus in 400 BCE and on to Rutherford in 1911 with the discovery of the nucleus are telling us that matter consists of atoms, and then it consists of atoms and subatomic particles, but it still consists of particles. De Broglie in 1923 says, I think matter has wave aspects, and as we saw in the previous lecture, he uses that to explain why Bohr's angular momentum quantization condition gives us the quantized energy levels in the Bohr atom. So what is it, wave or particle? Well, let's take a look more at wave interference and try to explore this wave-particle duality in a little bit more detail. So we're going to go to the big screen, and we're not going to do calculations this time. We're going to use the big screen, though, to illustrate these ideas of wave-particle duality. So if we were to do a two-slit experiment, that is, we send a beam of incoming light, or for that matter, electrons, because we're now concerned about whether light is a wave or a particle, and also whether matter is a wave or a particle, we send that beam into a barrier that has a couple of small slits in it. And that's exactly what I did with the laser beam in the apparatus I just showed you. If light consisted of particles, we would expect the particles to go straight through and form two bright spots on the screen. Now, those of you who are carefully remembering Lecture 43 on wave optics will say, wait a minute, aren't we going to get some diffraction patterns through the slits? Well, yes, and I'm assuming the slits are wide enough that we're not going to see individual diffraction very much. So we'll essentially get two bright spots on the screen opposite where those slits are. That's what we should see if light consists of particles. But if light consists of waves, here come the incoming wave crests. The waves pass through the slits. The slits act as sources of circular wave fronts by Huygens' principle. And so we see these circular wave fronts propagating outward until they hit the screen. And if you look, you'll see a pattern. You'll see a pattern in which there are places where wave crests cross. In between, wave troughs are crossing. So the wave is very low, very deep, very troughy there. It's very high, very cresty there. On the other hand, right there, a wave crest is meeting a wave trough, and there isn't much waviness left. And if I mark the lines where wave crests meet and where wave troughs meet, then I see I'm going to get regions of particularly intense waviness, and they're going to hit the screen. And if we're talking here about light, we're going to see bright spots on the screen. And that is exactly what we have over here in this apparatus in the experiment that I showed you in Lecture 43. We have on this screen, as the laser light from the laser at the far end comes through the slits and strikes the screen, we have on the screen that pattern of light, dark, light, dark, light, dark, light, dark that indicates that light is clearly a wave. So the two-slit experiment is a way of telling us whether light is a wave or light is a particle. Now, we are still wrestling, though, with this wave and particle duality. Which is it, wave or particle? Here are some results of two experiments. two virtually identical experiments. They're not quite two-slit experiments, although we could do two-slit experiments that would be analogous to what I'm showing you here, but these are slightly easier to do. These are experiments in which, on the left, a beam of light has been passed through a small circular aperture. And as we saw in Lecture 43, that results in a diffraction pattern, ultimately arising as waves from different parts of that aperture interfere with each other, and they produce these so-called diffraction rings, an effect we can see if the aperture size is comparable to the wavelength. That's for visible light. We've known about that for a long time because we've known that light is a wave. The pattern on the right, which looks very similar, is produced in almost the same way. It's produced by an electron beam going through basically a circular aperture. The aperture in this case is created by the spacing between atoms in a crystal, but it's the same idea. And what you are seeing here are these concentric diffraction rings associated with the wave nature of the electron interfering in some ways with itself and producing a wave pattern. Electrons are undergoing interference. Electrons interfere. Electrons also have a wave-like nature, just like light also has a particle-like nature. How on earth are we going to reconcile all this? How can we understand wave and particle simultaneously for both light and matter? That's what we've got to do. Let's go back to our big screen again. And let's now ask the question, which slit does the light photon go through? Because now we're asked to understand that light consists not only of waves, but also of particles called photons. Or, in principle, we could do this experiment with electrons, a beam of electrons, particles. And we're going to get this interference. And you might say, well, I'm going to really find out. I'm going to find out whether it's a wave or particle. I'm going to put a detector somewhere, and I'm going to watch one of these slits, and I'm going to see what slit the particle goes through. I mean, how does it do that? How does it know to interfere? How does it know to make this interference pattern? That's a wave thing. That's not a particle thing at all. It's a wave thing. How does it know? What slit does it go through? So I'm going to put a particle detector right there, and I'm going to catch that electron or that photon, and I'm going to see what happens. No luck. Because if I do that, I destroy the interference pattern completely. What I get instead is just what would happen if I had only one slit. Why do I destroy it? Well, I destroy it in a simple reason, because to detect a single particle, a single quantum of matter or energy, you can think of an electron as a kind of quantum of matter, you've got to interact with it, you've got to sort of absorb it and just basically destroy it. The fact is, if any experiment you do that attempts to detect those particles, you might want to not have a detector that absorbs them, but something that kind of sneaks and watches them go by and lets them go onto the screen, doesn't make any difference. Anything you do that tries to detect them and that is able to succeed will destroy the interference pattern, and you will see that the beam consists, you'll think, of particles. If you don't put a detector there, if you don't watch it, it behaves like waves. It can be particles, it can be waves. Which it is seems to depend on what you try to do. By the way, you might ask, well, what happens to this diffraction or this interference pattern if I really turn the intensity of the light way down? Maybe, after all, this light is the different photons are somehow getting through and they're messing each other up and interfering with each other. But it's not even that. Because if you turn this beam down so low that there's only one photon or one electron in the whole apparatus at a time, maybe you turn it down so low that only one photon goes through once an hour or one electron goes through once an hour, you still get the interference pattern. That single photon is somehow interfering with itself. That single photon is somehow going through both slits or sensing the presence of both slits somehow. How does it know to do that? And why can't you catch it in the act? As soon as you try to catch it in the act, you have detected it as a particle and you have ceased to have the wave behavior. But if you don't try to keep an eye on that electron, if you don't try to watch exactly what it's doing, if you don't try to make it behave like a classical particle following a particular trajectory, then it behaves like a wave and you see its wave nature. Very, very strange idea. An idea that was summarized by Niels Bohr and described in a way that allows us to reconcile these seemingly conflicting points of view. Here is what Bohr said. He described what he calls the principle of complementarity. He said the wave and particle aspects are complementary. They're two aspects of reality, and reality has both of them. And they're complementary in the sense that if you do a wave experiment, you see wave behavior. If you try to set up an interference experiment that's going to detect interference phenomena in either electrons or any other matter particles, for that matter, we've done it for whole atoms by now. If it's going to detect wave behavior, interference, for example, then you are going to see that wave behavior. If you do an experiment where you would expect to detect a particle, for example, Compton scattering, where a photon scatters, as we saw, off an electron, or putting any kind of particle detector that involves a single particle banging into something in that detector and making, say, an electrical signal, then you will detect the particle aspect of that behavior. What you will never be able to do is have it both ways. What you can't do is have a contradiction. You can't see both the wave and particle aspects of matter or light at the same time. You choose which you're going to see. You choose which way the matter or the light is going to behave. You can't have it both ways. You will never catch them in contradiction. So is light a wave or a particle? Is matter a wave or a particle? The answer is it's both, but never at the same time. And you determine which it will be. Now, this is a very strange idea. And it's a strange idea that's beginning to introduce in here a kind of fuzziness to nature at the quantum level. And we're going to spend the rest of this lecture exploring that fuzziness. Because we have these waves, we have these particles. What's the relationship between them? Well, the relationship between them is this. If you don't watch the system, a quantum system, it evolves like a wave. Anytime you try to detect particles, including looking on that screen in my interference experiment, maybe just with my eyes, maybe with some kind of electronic detector like in a digital camera, you are detecting individual particles. And here's the relationship. Where the wave that is describing those quantum particles has a large amplitude, you're more likely to find a particle. Or if you think of a whole beam of particles, where the wave has a large amplitude, there are likely to be lots of particles. So here I've got a picture of a wave that might describe some kind of quantum system. It might describe the waviness that I would calculate for the pattern on the screen of an interference experiment, for example. And you can see the wave starts out small, and it gets bigger, and then it gets small again, and then it gets bigger again. And if you think of a whole beam of particles that are being described by this wave, then what you would find is lots more particles bunched where the wave has big amplitude, and relatively few particles where the wave has small amplitude, and in fact, zero particles right where the wave has zero amplitude. Now, it's a little bit more complicated than amplitude. It's actually the square of the amplitude and some other mathematics. But basically, this is the idea. Where the wave is big, you're likely to find particles. And what this means is nature has become fundamentally probabilistic. Nature is no longer certain and deterministic, because we now have a probabilistic relationship between the waves, which are what we're able to calculate, and the sort of randomness of where these particles are going to appear. Reality is fundamentally probabilistic, and we've got a wave goodbye now to Newtonian determinism. Quantum mechanics, quantum physics, because of this dual wave-particle nature of both matter and light, becomes fundamentally probabilistic and, in some sense, indeterminate. People, philosophers, physicists have argued for decades, almost a century now, about this issue of no determinism in quantum physics. But every experiment we've done seems to point to the fact that the interpretation of quantum physics requires this probabilistic relationship between wave and particle. Let me give you an example here of building up the interference pattern, one particle at a time. What I'm doing here is throwing particles randomly on a screen, except the randomness isn't completely random. It's biased by where the calculation of the interference pattern, the wave calculation of the strength of the interference pattern, shows there should be the most particles. And what was at first a random pattern of dots is now beginning to emerge as a series of regions where there are more of these dots. And as we add more and more and more, that statistical pattern emerges. A single photon going through that two-slit apparatus wouldn't show us much at all. But when you send multiple photons, you gradually build up one particle at a time, this interference pattern. And that's what the statistical distribution of photons might look like on the screen of an interference pattern like I've shown you with my apparatus, except there are far fewer photons here than there are in a light beam. Remember, we did a calculation back when we introduced photons to talk about how the number of photons in a beam was probably pretty large if the beam had any appreciable power, at least at light frequencies. So we built up that interference pattern, and there's a photograph below it, a blown-up photograph of an actual interference pattern, and what you would see is the bright regions where lots and lots of photons have hit. They've been guided in some sense by these waves. Very strange probabilistic relationship between photons, particles, and waves, in this case the waves described by Maxwell's equations, the electromagnetic waves. A comparable relationship holds for the places where you would find electrons or atoms or protons or whatever small particles you want to do an interference experiment with, and the corresponding wave amplitude, except I haven't told you yet how to calculate that wave. That's going to be the subject of the next lecture. Now, all this waviness is giving us a kind of sense of vagueness about things. A wave is a little bit more vague than a particle. A particle is right here. I know where it is. And it used to be in classical physics, I also knew how the particle was moving, where it was headed, and how fast. Where's a wave? Well, a wave is kind of spread out. Stand by the beach and watch a wave coming in. Where's the wave? Well, it's everywhere. A wave has got a vagueness to its position, to where it is. And that vagueness translates into a vagueness in quantum physics. And that vagueness manifests itself as a very famous principle in modern physics, the uncertainty principle, formulated first by Werner Heisenberg in the 1920s. The uncertainty principle tells us quantitatively about this fundamental uncertainty in nature at the quantum level. And it's a fundamental uncertainty that arises ultimately from the fact that the nature of reality is dualistic. Reality, whether reality is light or electromagnetic radiation in general, or whether the reality is particles, the electrons, the protons, the atoms themselves, that reality has a dual nature, and out of that dual wave-particle nature is going to come the uncertainty principle. Let me give you some examples of how we understand the uncertainty principle. Here it is articulated in 1927 by Werner Heisenberg. And he said, it is impossible to determine simultaneously precise values for both a particle's position and momentum. Those are in some sense complementary properties. You can't measure them both simultaneously with perfect precision. There are a number of other uncertainty principles, a number of other so-called complementary variables in quantum physics, and most importantly, the most important other one, which I'll simply mention, is measuring energy and time. If you measure how long an atom has been in a particular state and you measure the energy of that state, there's an uncertainty, a kind of trade-off here. So there's the uncertainty principle as Heisenberg stated it. Here's how he thought about it with what he called a thought experiment. A thought experiment is an experiment a physicist sort of thinks up in his or her head, doesn't actually do the experiment, but uses the idea of this experiment. Maybe it's an experiment you couldn't even in practice do, but uses the idea of the experiment to come to some conclusion about the nature of reality. And Heisenberg's so-called quantum microscope is a famous thought experiment. So here Heisenberg is going to observe an electron. And his microscope consists of a light source, and the light source sends out a single photon. The photon bounces off the electron. The photon bounces into a detector. And we're going to use things like where the detector is positioned and so on, and how much energy is involved to measure the properties of the electron. We're going to try to figure out where it was and how fast it was moving. Now remember, photons have an energy, a minimum possible energy. One photon is the minimum amount of energy I can have at a frequency f, and the photon energy is E equals hf. So I've drawn the photon here as kind of a wiggly wave, but it's a very localized wiggly wave. It's a high-frequency wave, so I can get a lot of wiggles in there, and so I can have a nice wave, but it's still fairly localized. A high-frequency photon is easy to localize in this sense. And so that high-frequency photon also has high energy because E equals hf, and the high-frequency photon is going to hit the electron, it's going to bounce off, and it's going to go into the detector. And because the photon is quite localized, I can tell right where the electron was with considerable precision. But the problem is, as we've seen in the Compton effect, the photon is going to impart some energy to the electron. And I can't predict a priori how much energy it imparted to the electron. So no matter how the electron was moving before the photon hit it, after the photon hit it, it's got some other motion. So I have been able in this experiment to detect where the electron is, but I haven't been able to tell you how the electron was moving. I have one quantity measured about the electron, namely its position, but its motion, that is its velocity or its momentum, I have been unable to determine. Well, let me get around that. The problem here was that this photon had too high an energy. So let's use a photon of lower energy. So a photon of lower energy means a photon of lower frequency because of that quantization condition E equals hf. So I'm representing this photon of lower frequency by a wiggly wave, which has got to be more spread out in space to get those lower frequency, longer wavelength wiggles in. So now I'm going to hit the electron with this low energy photon. It's not going to impart much energy to the electron. It's hardly going to disturb the electron's velocity. But because this photon is not as localized, its wave nature is more spread out, even though I don't affect the electron's velocity, and so I can get a good measure of that velocity, I no longer know where the electron is. And so what I've seen in this experiment is a trade-off between trying to measure position accurately, which you can do, at the expense of losing information about motion, velocity, or in context of the uncertainty principle, particularly about momentum. On the other hand, I can measure precisely the particle's motion, how it's moving. I did that with the lower energy photon, which didn't disturb the motion as much. But then I didn't know much about where the electron was, because the photon itself was not localized. And so there's a trade-off. I can measure position very accurately with essentially no information about motion. I can measure motion very accurately with essentially no information about position. Or I can go anywhere in between, trading off equally. That's Heisenberg's quantum microscope thought experiment. Let's get quantitative with this idea. Here again is what Heisenberg says. It's impossible to determine simultaneously precise values for a particle's position and momentum. How does that manifest itself quantitatively? With this, it's not an equation, it's an inequality. It says delta P times delta X has got to be greater than or approximately equal to h bar. What does this equation mean? Delta P is the uncertainty in the particle's momentum, P equals mv, mass times velocity. Delta X is the uncertainty in its position. And the inequality says that that uncertainty can't be smaller than about Planck's constant divided by 2 pi, this h bar quantity. Now, you will see this written in several different ways. You might see it written with h bar over 2. You might see it written with h. The exact form of this uncertainty principle depends actually on the mathematical details of the shape of the wave that is describing the particle whose uncertainty you're talking about. So you will see different quantities on the right-hand side, and I just prefer to put h bar, and that's approximately correct. And whether it's exactly correct depends on the shape of this wave. So there's the uncertainty principle gotten quantified. Uncertainty principle says if you multiply the uncertainty in position and the uncertainty in momentum, it's got to be bigger than some certain value, which is basically Planck's constant. So if you make delta P very small, that means you're not at all uncertain about the momentum. You know the momentum, you know the motion accurately, then delta X has to be correspondingly big. If you make delta P 0, delta X becomes infinity. Similarly, if you make delta X very small so you know the position very accurately, then delta P becomes very large and you don't know the momentum at all. So there's that trade-off. Or you can make them some combination in between, but their product has to be bigger than basically Planck's constant, in this case, Planck's constant over 2 pi. So that's the uncertainty principle described quantitatively. Let's look at one other manifestation of the uncertainty principle. Let's say I take a beam of particles and I impinge it on a barrier with a hole in it. Now, if the hole is large compared to the wavelength, never mind that particles have wave-like properties, I'm not going to notice them. We saw that back in lecture 43. We see the wave properties of things only when they interact with systems that are comparable in size to the wavelength. So a beam of particles impinging on a barrier with a big hole is going to go through something like that. There's a large hole, so there's going to be very little diffraction, even though there's a wave nature to these particles. I don't care whether they're photons, light, or electrons, matter. Notice that the particles are going through and they're just heading right along in the horizontal direction. They basically have no vertical component of their momentum. So I know their vertical momentum very well. There's no uncertainty or almost no uncertainty in their vertical momentum, p sub y. By the way, the uncertainty principle applies individually to the different components of motion. There's a small variation in py, almost 0. I know the momentum in the vertical direction. I'm not talking about this momentum to the right, the momentum in the vertical direction. But the vertical position is quite uncertain. It's uncertain because I sent those particles through a big slit. So I don't know exactly where they are. So there's a trade-off. I've got a large delta y, a large uncertainty in position, a small uncertainty in momentum. I can solve that problem of a large uncertainty in position by making the slit smaller. But if I make the slit smaller, if it gets comparable to the wavelength of those particles, then they are going to undergo diffraction. And so the beam is going to spread out. And now I don't know the vertical momentum as well because the particles may have considerable vertical motion. So I've found out more about the vertical position, but I know less about the vertical momentum. Again, another manifestation of the uncertainty principle. The vertical position is well known in this case, but the momentum is very uncertain. Small delta y, large delta py in this case. Let's get philosophical about this idea, because it really is an idea with a lot of philosophy in it. The standard understanding of quantum physics, held by most but not all physicists and many but not all philosophers of science, is called the Copenhagen interpretation, because it's in Copenhagen where Niels Bohr held forth, and a lot of deliberation about this took place. And it says, it makes no sense to talk about things you can't measure. You can't measure simultaneously a particle's position and momentum, and therefore a particle doesn't have well-defined values of position and momentum, and you have to say goodbye not only to Newtonian determinism, but also to classical Newtonian trajectories. The idea of a particle that's here and moving with this speed, and then it's here and moving with this speed, or I should say velocity, and then it's here, gone. Because we can't simultaneously measure those things. Goodbye to classical determinism, and goodbye even to the ideas of Newtonian trajectories. Goodbye even to those nice circular orbits that Bohr wanted the electrons to have in the atom. Quantum mechanics is fuzzier than that. If this is bothering you, you're in good company. Heisenberg himself said, I remember discussions with Bohr which went through many hours till very late at night and ended almost in despair. And when at the end of the discussion I went alone for a walk in the neighboring park, I repeated to myself again and again the question, can nature possibly be as absurd as it seems to us in these atomic experiments? So Bohr and Heisenberg are wrestling with what you're wrestling with too. How can nature have this duality? How can what we think of as the way particles behave, baseballs, billiard balls, not be the way things happen at the quantum level? But it isn't. So let me summarize this very strange lecture. There's a wave-particle duality, and it's an essential aspect of physical reality. Light and matter both exhibit both wave and particle behaviors. The complementarity principle says no single experiment will reveal both aspects. You determine which you're going to see by what kind of experiment you want to do. The quantum world is indeterminate. The amplitude of the waviness determines the probability of finding particles, but not definitely deterministically. Only you're more likely to find the particle here, less likely to find it here, but you might find it in either place. The wave nature and matter light leads to the uncertainty principle. The uncertainty principle tells us there are these properties, momentum and position, energy and time, that we can't measure simultaneously. Their product of the uncertainties has to be bigger than some quantity on the order of Planck's constant. Particles don't have well-defined values of position and momentum, and quantum physics is really, really weird. Now, before we end, if you want to do some quantitative work with that, I will pull you back a little bit from that weirdness, because I want to show you that even though quantum mechanics is weird, and even though the uncertainty principle makes a lot of things uncertain, we can also find certainty, or at least some knowledge, from the uncertainty principle. So here's a challenge to you. Consider an atom. It's about 1/10 of a nanometer in diameter. That's about 2 Bohr radii in diameter, and Bohr radius is about the size of the atom. I would like you to find from just that fact and the uncertainty principle the minimum energy that an atomic electron could have. So think about that, work the calculation. I'll come back and give you the solution. Okay, here's the solution. We're uncertain. If we know that an electron is in the atom, then we know where it is to within about 1/10 of a nanometer. It's confined to this size, 1/10 of a nanometer. I'm going to call that the position uncertainty delta x. Never mind, we're in 3 dimensions and other complications. This is just a rough calculation. So there's an uncertainty in its momentum, because delta p, delta x is about equal to h bar. Delta p is h bar over delta x. I'm going to be really rough here. H bar is about 10 to the minus 34 in SI units. The uncertainty in position is 1/10 of a nanometer. That's about 10 to the minus 10 meters. It is 10 to the minus 10 meters. That comes out 10 to the minus 24 in the units of momentum, kilogram meters per second. Now, how could I be uncertain about the momentum? This means I can't know the momentum to better than that. Here's one way I can be uncertain about the momentum. I could know exactly the value of the momentum, the magnitude of it, but I could be uncertain in that I wouldn't know whether the electron was moving that way, say, or that way. So that's going to give me a kind of minimum possible value the momentum could have, because the difference between going this way and this way If it has momentum p going this way versus momentum p going this way, the difference between p and minus p is 2p. So the very minimum momentum this thing could have is twice the uncertain, delta p being twice the momentum itself. That would be the minimum possible momentum. And we know that kinetic energy is a half mv squared. P is mv. If you work a little classical physics and algebra on that, k becomes p squared over 2m. But the minimum p could be is delta p over 2, as we just showed. Divide that by 2m, square that delta p over 2, work out the numbers, and we get about 2 times 10 to the minus 19 joules for the minimum kinetic energy this thing could have. And that's about an electron volt. And what that calculation tells us is some really important knowledge. It tells us atomic-sized systems are going to have energies on the order of an electron volt. And that corresponds to photons in sort of the visible region of the spectrum, by E equals HF and lambda equals lambda times F equals C and all that. And so out of the uncertainty principle and our knowledge of roughly how big an atom is, we can tell something about roughly what the energies are involved in atomic transitions, and we can conclude that atoms are going to be sources largely of electromagnetic radiation in the visible region of the spectrum, as in fact we've seen they are.